We have been observing our home for 40 years now. In the last 20 of those, we have focused intensely on planet Earth. With new technologies and capabilities, accumulating a massive data that is now revealing a complex and ever-changing living planet. They've been watching us from space for the last 2 decades in high-resolution detail, watching our every move. The clouds and aerosols, winds and hurricanes, forests and cities, droughts and floods, the ocean currents and plankton, life in the ocean and on land. Land cover, aerosols, chlorophyll concentrations, wave heights, ozone concentrations, atmospheric moisture, the human footprint, sea level change, and temperatures and moisture in the soil. Now scientists have a high-definition data set spanning 2 decades to study and to learn from.
Well, NASA has a fleet of satellites that are always measuring Earth. They're looking at land, oceans, atmospheres, ice all together. The particular visualization represents the measurement of all life on Earth over 20 years. I personally find it mesmerizing. You're watching the Earth breathe here. The seasons are changing, ice is coming in and retreating. You can see the forests on land in green, expanding and contracting. You can see the deserts moving to the ocean. You can see biological deserts in the centers of the ocean, represented by blues and purples. And then as you look farther north in the Atlantic or towards Antarctica, you can see these greens and yellows. Explosion of life in the ocean, just like on land in the spring and summer. Incredible.
What we see for the first time is how the oceans and the land behave at the same time through time for 20 years. We've never had data like these before. Half of our photosynthesis occurs in the oceans and the other half on land. And having these data to show both at the same time, day after day, month after month, year after year for 20 years, is a great tool to study life on Earth. NASA has observed many aspects of the coupled land-ocean atmosphere system and how they interact. For example, we see that with warmer surface temperatures, the growing season is getting longer at higher northern latitudes, and spring is coming earlier. With satellite data, we're able to map this continuously across the Earth's surface and across the United States and across Alaska. Before that time, you had to rely where you had weather stations, and so you had points here, points there, but you never had continuous data like these. So using these data, we can look over very large areas and see regional effects, and sometimes these effects are positive in that nothing bad has happened. So it's only with these data we're able to do this over all these areas at the same time. And this is made possible by the use of Earth-viewing satellites, which orbit the Earth day after day, month after month, year after year. And these data are the basis for saying these things about Earth with confidence because we measure them.
The view from space is opened our eyes to so many different things. You can see transitions from La Nina to El Nino, represented by huge blooms of life across the Pacific Ocean at the equator, bigger and wider than the United States. You can see greening of the Arctic. You can see earlier summers, later winters, and you can see the emergence of harmful nuisance algae.
Charting the carbon dioxide cycle through the atmosphere, land, and ocean is essential to understanding the environmental changes that man is driving. Higher carbon dioxide, or CO2, in the Earth's atmosphere appears as red and yellow, while lower than average CO2 is shown as blue. The pulsing of the data is due to the day-night cycle of plant photosynthesis. As CO2 is lifted away from the surface, it is rapidly spread around the world by high-altitude winds. CO2 builds up in the northern hemisphere winter when plants are dormant. By summer, photosynthesis draws massive amounts of CO2 out of the atmosphere, resulting in lower CO2 throughout the northern hemisphere. The growth and decay of vegetation in the northern lands causes the seasonal change in atmospheric CO2. Long-term, however, it is human activity that is increasing overall CO2 levels.
So 2017 was the second warmest year ever recorded and the warmest non-El Nino year. That makes 5 of the warmest years ever recorded just since 2010. And NASA scientists have taken weather station data from over 6,000 stations, and we've connected the dots to understand how our Earth is changing. In this animation, you can see those warmer temperatures growing as we look at how much the high latitudes in places like Alaska have warmed since 1950. So across the globe, we're seeing a consistent trend towards warming, but with twice as much warming across the high latitudes like Alaska.
This rapid increase in overall global temperatures is clearly defined when satellite data is added to the model.
The ability to expand your senses into space, compress time, watch visualizations like these, see how the ecosystems of land, ocean, atmosphere, ice all interact, and then be able to rewind it and watch it again and again. It's amazing.
Ask any astronaut. When they look down at Earth, they see a single environment. No borders, no claims, just a single planet which we all have to rely on. With this data, scientists can check up on the health of the planet. One primary concern is the ozone layer.
So we know the Montreal Protocol was a huge success. This was signed in the late 1980s when scientists and policymakers from around the world gathered together to try to save the ozone layer.
The chemicals they regulated persist in the atmosphere for many decades. They thin the ozone layer and they create a seasonal hole over Antarctica. They basically take away part of our planet's natural sunscreen, and that increases the risk of skin cancer and damage to plants.
Scientists have projected the ozone hole will disappear almost completely by 2075, but several factors could delay that outcome.
There are some industrial compounds that are not banned by the Montreal Protocol, but as they enter the atmosphere, they will also hurt the ozone layer.
But the unregulated compounds have a short lifespan in the atmosphere, unlike the chlorofluorocarbons that were originally regulated. So they have a short-lived impact on ozone, and we don't think they'll delay recovery by more than a few years.
We projected by 2050, more than half of the ozone-depleting compounds in the atmosphere will come from long-lived substances banned by the protocol.
Because these compounds stay in the air for such a long time compared to the unregulated short-lived compounds, they will have a disproportionate and lingering impact on ozone. Any non-compliance with protocol can have significant consequences.
And the really big uncertainty in ozone layer recovery is climate change. There are many naturally produced ozone-depleting substances that are emitted by the oceans. And as the oceans continue to warm due to climate change, those emissions will increase, and that will further delay ozone recovery.
Scientists want to understand better how climate change will affect ozone recovery.
This is a hard problem. As a scientific community, we need to work on this major issue. We now have a powerful new tool to simulate atmosphere and its interaction with land and ocean to study this issue. And that's what we're going to do.
At the top of the world, however, the Arctic ice continues to shrink.
Sea ice is the ice that grows and melts within the Arctic Ocean. It grows in the wintertime when it gets cold, and melts through the summertime. And so it doesn't raise sea level, but it's very important for the global climate system because the ice is very bright and reflective. It reflects a lot of the sun's energy that comes in during the summertime and helps keep the Arctic cooler. It's like a refrigerator for the global climate system by keeping the globe cooler than it normally would be without sea ice. And as we lose the ice, it's like we're opening the refrigerator door and not cooling things as efficiently.
Constant observation since the 70s lets us see a trend.
The Arctic sea ice has been changing quite rapidly. We've seen it decline over 35 plus years of a record. The last 15 years particularly has been accelerating. So really it's become a matter of when, not if, we lose the Arctic sea ice because we have a lot of warmth in the Arctic. It's going to continue to warm. We're going to continue to melt sea ice. There's uncertainty as to exactly when that will happen, but sometime in the not too distant future, faster than we used to think, the Arctic Ocean will be substantially ice-free by the end of summer. Arctic sea ice is not the only place we're seeing big changes. We're also seeing big changes in Greenland, which is the big mass of ice on top of the continent, and we're seeing more and more melt. We're seeing ice calving off as icebergs. So we're seeing big masses of ice loss over the last several years. That means that that ice is going into the ocean. That's raising sea level. So that's going to have big impacts down the road as we continue to lose more and more ice from Greenland.
Ancient air bubbles trapped in ice enable us to step back in time and see what Earth's atmosphere and climate were like in the distant past. Today we stand on the threshold of a new geologic era which some term the Anthropocene, where the climate is very different to the one our ancestors knew.
We can see that a warmer world means that there's an impact for warming temperatures in the Arctic, melting sea ice. That sea ice leads to larger sea level rise. So NASA scientists are on the ground in airplanes and using our satellite data to understand how what starts in the Arctic doesn't actually stay in the Arctic.
The hope is that all this data collection will mean that real-world problems can be reassessed and new angles explored. A case in point, dolphin and whale stranding. Could this accumulated satellite data help address the problem? Cape Cod in the US state of Massachusetts is home to one of the most frequent marine mammal stranding sites in the world.
If we can get there quickly and provide supportive care, they have a much better prognosis in terms of survival.
Scientists know very little about why these mammals strand, and only a quick and efficient response in these events will save lives. Katie Moore works on the front line and has fine-tuned rescue efforts.
If we can develop an algorithm that pieces together the different variables that may be causing mass strandings or driving mass strandings, then we have the ability to then prevent them. We can have teams that are out on the shore looking for animals in those hot spots, knowing that all those variables have come together and this is the likely point in time where we're likely to see it. But we can also have teams ready to respond so that if they do strand, we're there that much faster and more animals will survive the event.
Marine biologists from the US Bureau of Ocean Energy Management were also looking at this problem.
For the large proportion of these strandings, the animals are across the ages, in pretty good health, and there's no really immediate evidence as to why they actually strand.
One possibility is geomagnetic perception, the ability to navigate using Earth's magnetic field, which is believed to be used by marine mammals. Could changes in the magnetic field confuse the animal? Geomagnetic pulses or storms can be caused by space weather.
Geomagnetic perception is one of the theories, and I thought, well, if a magnetometer can pick it up, maybe the animals actually can pick it up.
Dr. Reed consulted with NASA at the Goddard Space Flight Center.
The coolest thing was that we realized that nobody had really taken a cold, hard data science analysis look at the problems.
What we were trying to look at here was if there was a potential driver or relationship or correlation between the occurrence of mass strandings and any solar activity.
The data that we have correlated or analyzed so far is information about the local geomagnetic conditions. We have long data records from geophysical observatories of the local geomagnetic field variations and marine mammal stranding.
Their analysis was inconclusive. They needed more data from other environmental conditions.
Easy fixed correlation between a geomagnetic pulse and, a stranding doesn't seem to be very evident, but what it does show is that there are multiple variables involved in this equation, and that the geomagnetic storms could just be one very small part of it. Significant still, but it looks like there are multiple oceanographic and environmental elements.
With more data in hand, it was time to expand the team. They recruited statisticians and the expertise of NASA Earth Science data analyst and oceanographer Erdem Karakolu.
A data set, no matter its shape or content, always has a story to tell. Trying to figure out how different data are connected, I think, require a wide diversity of skills and background knowledge.
For example, I'll be explaining how a mass stranding occurs and how we respond to try and understand why I'm presenting the data in a certain way. And my colleagues from NASA will look at me and ask questions that I wouldn't think to ask because I take for granted my understanding, and they're coming at it from a totally new angle with no background.
These data sets may reveal a pattern, allowing scientists to predict the likelihood and location of mass stranding before it happens.
We've really just sort of slowly peeled the first layer of this onion back. And I think that there's so many more layers that still need to be addressed and looked at. And I hope that we can actually find additional collaborators, additional funding partners to really bring all the data that's really available to really give this the study and the scrutiny that it deserves.
And we are also going to make all these data sets available to the entire scientific community so that we can utilize the entire scientific community to take attack and approach this problem.
I think that there will be other things to take and run with, get new ideas, maybe add more data. And I'm hoping also that it will be a model for how projects can then be open to the wider public.
The ability to release animals after they've stranded is tremendous. When we do that, that's the best feeling in the world after all of that hard work.
Those questions that seem unanswerable, if you give them time and support and effort and put people on them, we can do amazing things.
Data from satellites reveals the interconnection between air, sea, and land. This is a visualization of 3 aerosols: dust, smoke, and sea salt. The Calypso satellite data reveals in 3D how dust from the arid Sahara Desert is lifted by the winds each year and transported nearly 5,000 kilometers across the Atlantic Ocean. Some of it settles in the Amazon basin, the largest rainforest on the planet. Sahara dust contains phosphorus, an important nutrient for plants. Calypso shows that on average, 182 million tons of dust leaves Africa each year. When the Sahel was dry, the dust transport to the Amazon in the next year would increase. When it was wet, dust transport would decrease. We can now track global precipitation, wind currents, cloud cover, and ocean temperature. Satellites have detected a shift in phytoplankton populations across the planet's 5 great ocean basins, showing the expansion of biological deserts where little life thrives. Diatoms are one of the most abundant types of marine phytoplankton, but a new 15-year-long NASA study reveals global populations have declined. Diatoms, like all phytoplankton, have chlorophyll, the same photosynthesizing pigment as plants. They occupy the surface of the ocean, where they harvest light from the sun. In large numbers, diatoms form colorful swirling blooms that can be seen from space. According to the study, significant decreases in populations, shown here in red, are mainly in the northern hemisphere.
Diatoms rely on nutrients such as nitrate, silicate, and iron to reach the surface layer where they live. What the study shows is that the availability of these nutrients has changed due to the way they cycle within the water column.
Diatoms occupy the surface area of the ocean called the mixed layer. Nutrients collect on the ocean floor and are cycled up to this layer. Various physical forces can cause the depth of the mixed layer to become shallower, so that fewer nutrients reach the diatoms. Without these, their populations decline. This map shows areas on the globe where the depth of the mixed layer shallowed.
It's hard to pinpoint exactly why this change have happened. Things like wind, circulation, and temperature can affect the way these nutrients are brought to the surface layer. We hope a longer study can yield more information on whether these changes are in fact a trend or variability.
Next-generation satellites are reaching orbit now to continue this important work. They will collect data, maintain observation continuity, and allow scientists to track the changes in our environment. They can then model dynamic simulations to better understand this unique planet and the myriad of life forms that rely on it. The tenuous envelope of gas surrounding our planet is an unbelievably complex machine that protects us from the vacuum of space, shelters us from harmful radiation, and allows us and the biosphere to breathe. It is our atmosphere, and we need to learn much more about it so we can take better care of it. Soon the European Space Agency ESA will launch its new Earth observation satellite called Aeolus. Using cutting-edge laser technology, Aeolus will provide near real-time observations of wind profiles across the globe. These will improve the accuracy of numerical weather prediction and climate modeling and advance our understanding of global atmospheric dynamics.
Aeolus is one of the Earth explorers that is going to look at the Earth, trying to understand the wind profiles globally. And that's a first, it doesn't exist yet. The whole idea was that we only have wind measurements on very different small spots on the Earth, and we didn't have it globally. So the mission scientists had been asking for this because it's a gap in our measurement system.
The mission aims to expand our knowledge of our atmosphere and weather systems. Aeolus will achieve this by providing global observations of wind profiles from space, providing data which has never been available before.
It's unknown ground. It's what we call uncharted territory. So we are the first agency trying to get a satellite in orbit that looks at the Earth with a laser and trying to understand the wind profile, so the direction, the height and the wind speed. And therefore improving the weather forecast. Because nowadays we only have at single points balloons that measure the wind, or airplanes that give us some data, or at fixed points, at discrete points. This will look down to the Earth in a polar orbit, will dump every 90 minutes the data to Svalbard. That will be distributed to all the European meteorological institutes. And then when you're sitting at home on your couch, you watch the television and you see a weather forecast that is much better than we have it today.
Aeolus will fly in a sun-synchronized polar orbit 320 kilometers above Earth's surface. Its data will be sent to ESA's Svalbard ground station, located in the archipelago halfway between Norway and the North Pole, every 90 minutes. The satellite's main instrument is Aladdin.
Yes, the way the Aladdin instrument works is to eject an ultraviolet beam down through the atmosphere, and then particles of moisture in the atmosphere at various levels are in motion because of the wind, and the system measures the backscatter from those particles using the Doppler effect and can detect the wind speed at the various altitudes, and that's the way the system operates.
The development of Aeolus has been a long and difficult process, with new and cutting-edge technologies designed, developed and tested on the ground.
It has been a very difficult challenge, let's say. It's a long life, because it exists already for 16 years, the program. And when we first had the part of the instrument, when we switched it on, it worked. Then we put it in vacuum and it stopped working. And no one had realized that we needed oxygen inside the satellite to keep the laser active. So it was quite a challenge, so we had to develop a whole new set of techniques. It's maybe a bit too detailed to go in all the details, but as a lot of technology has been developed, put in this nice little satellite which is behind me.
Aeolus is another ESA Earth Explorer mission aimed at pioneering new technology while providing useful data about our ecosystem. It showcases the technological expertise of the European space industry and ESA's objective of monitoring and understanding the planet we all live on.
The main challenge for us has been within the development of the Aladdin instrument. There's a very high-powered ultraviolet laser system in there that is an inherent part of the instrument. And the technology behind that laser system, the development of a stable laser, high-powered laser beam, and the optics that then focus and divert that beam through the system is very critical, and that's been a very key part of the development. After many years and much hard work across the European industry, we've overcome those problems. We've got some new development through coating technology on the optical surfaces to protect them. And we've now got a stable system that's been fully tested on the ground, and we're ready to go.
The tracking of air pollution is also part of the European Union's Earth observation program, Copernicus. One of the satellites that gave scientists massive amounts of data on atmospheric pollution was ENVISAT. This satellite used several spectrometers to detect ozone and trace gases in our atmosphere. The latest satellite, the Sentinel-5 precursor mission, was recently launched and builds on that legacy of ENVISAT.
So we started this precursor mission because the scientists wanted continuity of data. At the moment we only have one spacecraft doing that job for us, which is OMI, and OMI is coming towards the end of its lifetime. The next missions that will do this job is Sentinel-4 on meta-upcycling, which will only be launched in early 20s. In the meantime, to ensure a continuity of data, we need Sentinel-5 precursor. It will be the only such mission doing this job until then.
Sentinel-5B is a precursor to the Sentinel-5 mission, which should be launched around 2021. But it's not only a precursor, it's also a gap filler, because it's filling the gap based on the data that we have coming from Gomez, Kirmaki and OMI measurements towards this future Sentinel-4 and Sentinel-5 missions.
Sentinel-5P is the first atmospheric chemistry mission within Copernicus. Its main instrument is a state-of-the-art spectrometer called TROPOMI, which will be used to detect trace gases in our atmosphere. With Sentinel-5P and TROPOMI, Copernicus will dramatically improve operational atmospheric services. The Sentinel-5P satellite is a timely replacement for the ERS and ENVISAT after it stopped working. There was an urgent need to fill the gap in observing air quality and air pollution. Furthermore, according to the World Health Organization, air pollution is responsible for over 3.7 million premature deaths worldwide every year. But the health costs are even greater, as many people suffer from non-lethal afflictions either caused or aggravated by breathing polluted air. Another major health concern on which Sentinel-5P is gathering data is the ozone in our atmosphere. When that ozone is depleted, ultraviolet light from the sun is no longer filtered. Increased exposure to UV light can cause skin cancer, immune system damage, and other ailments in humans.
The TROPOMI data will be used operationally, so it will be used to improve the air quality forecasts. And air quality forecasts are of course important for people who are vulnerable to pollution, but also for the general public in case of big smog events. What we can do with the TROPOMI data is we can look at the emissions of pollutants. And when you see them changing over time, that is very important because we can see if certain policy measures have the right impact or where we see still increases and still have to do more to reduce the polluting emissions.
A decline in air quality such as smog poses massive risks for people's health. And one of the main contributors to climate change is the pollution of our atmosphere by greenhouse gases such as CO2 and methane. This is why measurements on air pollution need to be undertaken everywhere. Like here, for instance, with a mobile measurement station at the University of Bremen. It detects smog and industrial emissions. These local measurements supplement and validate the global observations from satellites, which in turn are needed for scientists to study the air we breathe and the planet we live on.
Well, the satellites are a key information base and knowledge base for the study of atmospheric physics, chemistry and meteorology. It's essential data because we need to know not just what's coming out at a given place, but we need to know where it's going, where it's depositing at the surface, how it's being transformed, is it going to be taken up by clouds and rained out, if so where? And this whole transport and transformation process is a complex business. In general, we have this problem of unambiguously identifying anthropogenic impact from natural phenomena or natural behavior in this complex system and how we're modifying it. So this is the challenge for the science, which is a necessary prerequisite to enable good legislation and ultimately sustainable development. So in this context, measurements from space are essential because they provide us with the global picture, or from the local to the global scale.
The Sentinel-5P mission will have quite some improvements as compared to previous missions. For example, if you look at the spatial resolution, we will break a record, namely we will look at city scale, because the nadir pixel size will be as low as 3.5 kilometers times 7 kilometers. So we can then investigate small-scale features over big cities and city agglomerates, for example.
The mission will monitor the atmosphere using the TROPOME spectrometer to monitor various trace gases in our atmosphere and reduce data gaps between ENVISAT and Sentinel-5. By combining satellite data with the local measurements on the ground, scientists can properly monitor air pollution and how it impacts us and our planet.
We have lots to understand to assess the impact. Ultimately, more pollution is bad for health, bad for people, and the estimates are somewhere between 3 and 7 million people a year die prematurely from air pollution. This is a large number of people.
At the forefront of Earth observation, the European Space Agency helps us to understand climate change and pollution by giving scientists and policymakers the data that can drive legislation.
These atmospheric measurements are extremely important for mankind. First of all, to see how our planet changes in terms of climate, but also to see how air quality changes in different places and over time. We have highly polluted areas which are, of course, transporting pollution from one place to the other. So these fluxes of pollution or gases is very important to monitor. But also, if you take Europe, for example, Europe has introduced very strong legislation and regulations in order to reduce greenhouse gas emissions. And this has also to be verified, and these satellites are a very good measure or very good way of making sure that these reductions are taking place at a large scale.
In the early 2020s, the space component of the Copernicus atmospheric services will be extended through the addition of Sentinel-4 and 5 missions. Sentinel-4 will be a geostationary mission, whereas Sentinel-5 will be a low-polar orbiting mission like Sentinel-5P. Atmospheric services are part of the Copernicus portfolio, which comprises 6 main themes: marine, land, emergency, security, climate, and atmosphere, giving a complete overview of our planet's health and its evolutions.
Can have a lot of practical applications using the data from the Sentinel-5P mission. One idea would be perhaps if we look at the harmful UV radiation, you could set up UV radiation services so that people on the street, so to speak, in the sun like today, could inform themselves how harmful it is to receive this short-wave ultraviolet radiation.
The Sentinel-5 precursor data will be combined with models and other data to develop targeted services, and they will be available as apps, social media information, or web services, so that a lot of people can choose their way they want to be informed about the environment.
Atmospheric measurements are important because especially these measurements that are done by Sentinel-5 precursor, like tropospheric ozone, information about nitrogen dioxide, sulfur dioxide, also information about aerosols, particulate matter. they have impact on the health of people. They can impact the people who have problems with their hearts or with their lungs. And as it has been shown, there are more than 400,000 premature deaths in the European Commissioning based on exposure to air pollution.
Air quality in Europe in particular, but also in the US and in Japan, got much better over the last years. That's a really big improvement. And at the same time, air quality in the developing countries, in particular in Asia, has gotten worse because they use much more energy nowadays, and that's a big source of air pollution. Also, if they are using more cars, that will pollute the air more. So it's different, depends on where you live. In some places air quality gets better, in other places air quality gets worse. I should add that in the last 3 years, air quality in China has improved because they are very ambitious about that and have very strict rules. So they are trying to follow the European or United States path in improving air quality with better technology.
Observation from space is just one of several methods of measuring atmospheric pollution. Satellites provide the data, although they need to be calibrated with measurements on the ground.
So we are offering a comprehensive analysis, integrating data at different scales. So we are using observations, we are combined with modeling, with satellite data, and all this information is complementing each other. This is the good thing of this kind of analysis. Satellite have the advantage of providing a global picture. Trends, you can study trends very well, how the main flows are taking place. But satellite data, they don't have the resolution to get in detail in the individual processes. So here, with our in situ measurements, we are getting in one particular point, and we get deeply in the detail.
The satellite gives these beautiful maps, but you can only use them really if you have a validation measurement to compare to, and this needs to be a very good measurement, and this needs to be taken on the ground. That's very important for us because we need to be very confident of the satellite data. And once you have launched the satellite, it's out of your hands and you cannot bring it to the lab and double check and test it. It's there and you need to trust the data, and the only way to get this confidence in the data is by comparison to other measurements.
Other forms of atmospheric pollution, such as the exhausting of carbon dioxide, methane and ozone, contribute greatly to climate change.
Well, I think basically it's often the case that our models, which are extremely complex and good tools, often don't necessarily have the right physics or chemistry in them to be able to predict what's going on in the future. So a lot of the time in atmospheric science, we've been making discoveries. Back in the late 19th century, early 20th century, the discovery of the stratosphere was a complete surprise at the time, or fairly surprising. The fact that temperature increases above the tropopause. This was a surprising discovery, and really that's been typical. We didn't expect summer smog. We don't understand why in Paris there was a really big smog a couple of years ago in spite of improvements of legislation. This winter we had in London a smog which is maybe being attributed to excessive wood burning recently. So there's a lot of things although we're getting over the last 25 years much better information, but the satellites in particular tell us ultimately, or could tell us ultimately, what the source strengths are and enable us to follow the information, and thereby, together with models, give really good prediction for people about the air quality that they're receiving.
The Copernicus program is very important for Europe and for the world. First of all, the Copernicus program is providing free data to everyone at any place in the world. So many users, not only in Europe, but also in America, in Asia, are using our data in a very large scale and very significantly. So therefore, Copernicus is really monitoring the health of our planet from all dimensions. The atmosphere, the oceans, the land surface, the ice caps, and this whole system of the Earth composed of these components is monitored constantly with Copernicus. And therefore it is really important to see what is the state of our planet and how it will evolve in the future.
Well, the data can be used for different applications. So, for example, for the air quality forecasts. It's also used by KNMI, for example, for the UV forecasts. And we also use it to warn the aviation for volcanic ash plumes. On top of that, the data will also be used by scientists around the world to study the atmosphere and to study how man is changing the atmosphere over time. Continuous monitoring is very important, especially when you're looking at slow changes, and an overlap between the data is then really necessary to be able to glue these different data sets together. In the 19s, for example, for the pollution, it's very important to maintain these valuable data records and to extend them into the future.
Well, the data is important for our climate research and also for our environment, because the air we breathe, it could be changed due to all sorts of pollution events. And then a second example is that we need to monitor our ozone layer. Since ozone is destroyed due to chlorofluorocarbons, Sentinel-5P will have also the role to monitor the further evolution of the ozone layer.
Mankind can halt the pollution of our atmosphere with good legislation. The European Space Agency, ESA, works tirelessly to monitor our planet and the air we breathe.
We need a future where we, with so many people on the Earth, are in a position to maintain a good quality of living for human beings, but also for the biosphere.
Set the controls for the heart of the sun. It's a dramatic statement familiar from movies and music, but now a new mission really is ready to plunge into the atmosphere of a star. Not just any star, our star, the Sun. 60 years in the making, the Parker Solar Probe is primed to reveal the true nature of the heart of our solar system and the source of the solar winds. Weighing just 685 kilograms, the solar probe was launched aboard a ULA Delta IV heavy rocket. Its thrust of 9,700 kilonewtons may seem like overkill, but the Parker probe has to travel faster than anything before. As a matter of fact, it will be the fastest man-made object ever launched.
Parker's solar probe really is a historic mission. It was first dreamed of in 1958, and it's remained the highest priority mission throughout that period. The reason it hasn't flown is just because it's taken a while for technology to catch up with the dreams that we had for this amazing mission.
Destined for the Sun, our star, This probe is the realization of a dream that has been evolving over decades through the talents of hundreds of dedicated people.
After working on this for 10 years, it is really a pleasure to see it kind of actually coming to fruition. To be one small part of this huge engineering team that is making science dreams come true is just amazing. I can't wait to rewrite textbooks and change the way we look at the sun forever. I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy all that Solar Probe brings us.
This is a 60-year journey that people have gone on to make Parker Solar Probe a reality. And to be there at the finish line, that is definitely the coolest thing about my job.
Several questions arise. How did this project get started? Who was behind it? And why is it called the Parker Solar Probe? It's because of this man.
The Parker Solar Probe is the first mission ever to be named after a living person, our own University of Chicago astrophysicist Eugene Parker.
Born 1927 in Houghton, Michigan, Gene Parker gained his PhD from Caltech in 1951. By 1958, he had developed his theory on the supersonic solar winds and predicted the shape of the solar magnetic field in the outer solar system, which now bears his name, the Parker Spiral.
So Gene Parker had graduated in physics and had a hard time actually getting a job. So he was first doing some researching at University of Utah when he was then invited to come to Chicago. He was not sure he was going to make it in the field. When he wrote his paper, it didn't help that the referees were not in agreement with him and didn't really want to publish his work. So he had lots of challenges early on, but he was right. And this is one of the things that first helped him, be the person that we all recognize as this amazing role model to all physicists, but also the power of science being right or wrong due to experiments. So what vindicated him was not just having Chandrasekhar, for example, helped him publish his article, but what really made him who he is in the history of science is the fact that the measurements showed him right.
Eugene Parker has received many accolades over his career, including the National Medal of Science for Physical Science and the title of S. Chandrasekhar Distinguished Service Professor Emeritus at the University of Chicago.
So in 1958, Gene Parker realized that the sun has a magnetic field and it will have a structure around the solar system that will be populated by what we call plasma. So these are hot particles that are flying from the sun all the way to the edge of the solar system. This is what he called the solar wind. So the solar wind is a structure generated by the sun, which basically envelops the whole of our solar system all the way to the edge. And it has been studied all the way to the edge of the solar system with, for example, the Voyager probes, which are now crossing into what's outside of the solar system, which is the furthest that man has ever been, or any man-made machines have ever reached across the solar system.
I laugh about this because I remember how upset some people were. They insisted I made a mathematical error, and I would reply, well, here you are. Here's 5 lines of algebra. You say I made a mistake. Show me. And it's amazing the number of people that just couldn't let go of the old ideas. They've been working on the spacecraft for several years, and one day the phone rang, and it was a guy that I know said, we're talking about putting your name on the Solar Probe, Plus it was called. And did I object? And I sort of said, no, I feel rather flattered. So he said, okay, that's what we'll do.
While the success of this mission bearing his name will not be known for many years to come, all the effort is sure to be worthwhile. The advances in engineering required to make this mission successful have been far-reaching and at times ingenious. That's because the speeds required to reach the sun are mind-boggling in themselves.
The solar probe will be reaching the closest ever to the sun and moving the fastest and reaching the hottest regions of the solar system. It's so fast that it could go from Chicago to Beijing in less than 1 minute.
There are many enabling technologies. The solar arrays were very important. The autonomy was very important. One of the ones that was obviously also critical is the heat shield. And developing the technology to actually protect the probe at the sun.
The Parker Solar Probe is a technological marvel. The thermal protection system, the heat shield, will be glowing cherry red. The front surface of that will be 2,500 degrees Fahrenheit, while the spacecraft remains 85 degrees, roughly a warm day in Florida. The material sciences just didn't exist in the 60s and 70s, and so the carbon, which came out of frankly the military, looking for lightweight, stiff, strong structures, were the precursors to your tennis rackets and golf clubs, which are now the precursor to the carbon-carbon technologies that we have on Parker Solar Probe.
Temperatures so close to a star can reach a phenomenal range. Serious sun screening is required.
And a sandwich panel is a lot like a honeycomb panel you find in a traditional spacecraft or on airplanes. You have two outer face sheets, and then you have a core. In this case, the two outer face sheets are carbon-carbon composite, which is a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated. And then the inside is a carbon foam. So the Parker Solar Probe heat shield has a white coating that's on the sun-facing surface of this giant frisbee that's protecting the rest of the spacecraft. And that white coating was specially designed here at the lab in collaboration with RED and the Space Department, as well as the Whiting School at Johns Hopkins proper, to actually work at the sun. This was specifically designed for Solar Probe. And the concept is basically you'd rather be in a white car on a hot day than a black car on a hot day. It's just that it just knocks down the heat that much more. And so it's helping us stay cool at the sun. That titanium truss was also specially designed for Solar Probe. It's actually a really neat piece. It's a welded titanium truss that's about 4 feet tall, but it only weighs about 50 pounds. And the key there is we're trying to minimize the conduction between the heat shield and the spacecraft. So you want to have as little stuff there as possible.
The hottest environments in the solar system will be probed by this mission, and its instruments that will be measuring all the different properties of the solar corona are protected by a shield, a state-of-the-art shield developed by NASA, which would make Captain America very envious. This shield keeps the instruments behind from being cooked every time the probe gets really close to the sun. So the shield made of reinforced carbon is really something that is very recent technology, and only now we can actually get that close to the sun and really verify some of the predictions that Gene Parker has made over his whole lifetime of trying to understand the solar wind.
Earlier iterations of this spacecraft design were predicated on a nuclear power supply. That idea was dropped in favor of solar panels, which brought their own design difficulties so close to the sun.
Parker Solar Probe needs electrical energy to operate. Like any other satellite, or most other satellites, the spacecraft has solar arrays. But unlike other satellites, we have to generate electricity very close to the sun. For every watt of electrical energy we generate, we have to dissipate 13 watts of thermal energy. To do that, we need a cooling system, and we have a cooling system that's much like you'd find in your car. There are 2 water pumps in the system that pump water through the solar arrays and up into radiators. Those radiators radiate the energy to deep space, which is very cold, as opposed to like a car where it would be radiated to air.
When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool, and that's most of the stuff is on the bus.
If you look at the science data, there's a big gap, and that gap is where Solar Probe is going. We're going to fill that gap of scientific knowledge. So it's true exploration. I mean, in that, and we're not following somebody. We're be the first spacecraft, the first people to go there. So what'll be interesting is not the answers to the science questions. What'll be interesting is the new questions that Solar Probe forces us to ask. Because one thing we're pretty sure of is that probably have it somewhat wrong. Solar Probe will teach us what's right. And that'll generate many, many more questions and many more missions to come.
NASA's Parker Solar Probe will soon fly closer to the Sun than any spacecraft before it, some 4 million miles from the visible surface. But getting that close to the Sun requires some fancy orbital mechanics and a dash of brute force. Why is it so hard to get to the Sun?
Another reason Parker Solar Probe wasn't launched in the last 60 years is that getting so close to the Sun is hard. It takes a huge amount of energy to get to where we want to go. When a satellite lifts off the Earth, it carries the Earth's velocity around the solar system. So the Earth is moving at about 30 kilometers per second around the solar system.
Of all the space missions I've worked on, Parker Solar Probe is the most challenging and complex mission to design and to fly. The launch energy required to reach the Sun is 55 times of required to get to the Mars and 2 times to Pluto.
Traveling so close to a star can also affect communications with Earth. In such a dangerous environment, engineers had to design software with serious smarts.
So Parker Solar Probe uses a sophisticated rule-based autonomy system to protect itself. For long periods of time, the spacecraft can't communicate to the Earth, and it needs to take care of itself. So the engineers during the development phase spent a lot of time thinking about what faults could affect Parker Solar Probe and came up with solutions for those faults. Those solutions are encoded in this rule-based autonomy system so that even if there's a fault on orbit, which of course we hope there isn't, the system can take care of itself. One of the most common questions I get are, what happens if the spacecraft gets hit by a solar flare or gets hit by a coronal mass ejection? Will it be destroyed? That's a very common question. And what I tell people is the science community will be elated if we were to get hit by a solar flare or a coronal mass ejection. They're very dramatic events when you look at them in a telescope or during an eclipse. But in the reality, they're very ethereal. The density of the particles isn't so high from the point where it could actually cause damage to the spacecraft. But the instruments aboard the spacecraft, the electromagnetic field instruments, the high-energy particle instruments, the plasma instruments, and the visible white light sensors will see this event. And how dramatic would that be to see a solar flare coming at you and to fly right through it?
The sensor suite on board the Parker Solar Probe is indeed impressive. Each was designed to withstand the harsh radiation and temperatures to measure the particles, electric and magnetic fields of the solar wind. There is also an imaging instrument on the spacecraft called WISPER.
The WISPER instrument is the only imaging instrument on the Parker Solar Probe, and it is looking in the direction that the spacecraft is traveling. And what it sees is light scattered by the dust that's in orbit about the Sun. But then, once we remove that, what we see is the light scattered by the electrons in the corona, in the solar wind. These measurements that we're making from the WISPER instrument have been made before by other instruments from 1AU, from the distance of the Earth, about 100 million miles from the Sun. By getting closer, we're increasing then the ability to see what's really close to the Sun. The fact that you're close means that you don't have all this material that's in between you and the and the object that you're really interested in. And that contributes to background noise. And so you're looking at something that's much more pristine. You're looking at just that object all by itself.
We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield. And then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight and they get very hot. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. Then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team, will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly the 3D visual models of the coronal magnetic field. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field, and together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what Fields will do. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona has just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
The other science packages aboard Parker include SWEEP and ISIS, designed to study the particles emitted in the solar wind.
ISIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ISIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle.
The SWEEP investigation consists of 3 separate instruments and a central electronics box. Most of the instruments within SWEEP sit on either side of the spacecraft, stare out over the entire sky, and make maps of all the different particles and what energies they're moving at, what types of particles they are. The purpose of SWEEP is to measure the bulk of the solar wind and the solar atmosphere. One of the biggest questions we want to resolve with Solar Probe is how the corona and the solar wind are heated. In order to do that, we need to see if there are waves that are coming from the sun and depositing energy within the solar atmosphere and in the solar wind. So we have a series of sensors across the spacecraft that will collect individual particles, electrons, fully ionized hydrogen and helium, which we call protons and alphas, and other minor ions, and make maps of the number of particles as a function of their speed and energy and type. We take those maps on the ground and we can interpret them to figure out the temperature, the density, the pressure of the solar wind and the solar atmosphere.
Learning the secrets of our star, the Sun, will help us understand the nature of the solar system and its all-embracing influence on our world. But the Parker Solar Probe is not the only mission destined for that star. The European Space Agency is also in the game. In collaboration with NASA, the Solar Orbiter is set to launch very soon and will be joining Parker in its quest for knowledge. The orbiter will fly an elliptical orbit within the orbit of Venus, but on a much greater inclination off the ecliptic, giving it access to the poles of the Sun. Unlike the Parker probe, the orbiter's main observation instruments will peer through the solar shield at a safe distance, then reconfigure when making a closer approach. Together, they will reveal the secrets of our closest star, the Sun. It won't be long now before you too can enjoy a view like this. Economy or business class? There will be a variety of choices of carrier and cabin. The view will be spectacular. This is the traditional way to orbit, a Russian Soyuz launched from Kazakhstan. NASA has to pay in the area of $70 million per seat return trip, and prices are about to go up. Only the Chinese have an alternative launch system. Very shortly, there will be 2 carriers taking tourists into space on suborbital flights. Blue Origin will probably launch first with their capsule and reusable launcher. Next will be Virgin Galactic and their suborbital space plane, launched from beneath a carrier aircraft and landing like one too, although to what altitude is still not known. Then you have America's return to space with its 2 commercial partners. Boeing have their CST Starliner, the first launch-capable capsule already off the assembly line. Looking every bit like an Apollo spacecraft, it will be able to ferry crew to and from the ISS. An unmanned test launch to the space station is imminent, and the crew has been picked to undertake the first few missions. Their standout competitors are SpaceX and their manned Dragon capsule, performing the same vital service. They're hedging their bets in the tourist sector as well, with their BFR concept naming their first paying customer.
Thank you, Elon. Thank you, everyone. Wow. I am from Japan. My name is Yusaku Maezawa. You can call me MZ, please.
After the success of the Falcon Heavy maiden launch, SpaceX is ramping up design and construction of its even larger rocket ship to Mars. However, the two other commercial entities aren't resting on their launchers either. Jeff Bezos' Blue Origin has developed its BE-4 engine to power an orbital delivery system, and they have the US Air Force on board. Not to be left out of the market, Virgin has also developed a small payload orbital system, Virgin Orbit, with its Launcher 1. Flown to 35,000 feet, slung beneath Cosmic Girl, a Virgin 747, the two-stage rocket can lift up to 500 kilograms into orbit and an inclination up to 120 degrees. Dream Chaser is still in the running with its pilotless shuttle, still under development for long-duration orbits. The late Microsoft founder Paul Allen's company Stratolaunch has unveiled the largest aircraft in the world, a scaled-up airborne launch platform with multiple payloads from the existing Pegasus rocket to a medium and heavy launch vehicle and a reusable spaceplane in the future. In the meantime, there is no shortage of conventional launch systems competing for their share of the market. From the USA, Europe, China, India, Japan, even Israel and New Zealand. The key to any launch system is, of course, the engine. The smaller, lighter, and more powerful, the better. They pose many design problems. Fuel type, reignitable, chamber pressure limits, sea level or vacuum exhaust nozzle shape, but above all, reliability and cost. This is the Avio rocket factory in Colleferro, Italy. Here, engineers are developing the carbon fiber casing for the solid propellant rocket stages of ESA's new Vega-C launcher. To build them, 5,000 kilometers of carbon fiber impregnated with epoxy resin is wound around a pre-made metal mandrel. This produces the very lightweight but sturdy casings for the first, second, and third stages of the Vega launcher. These casings are later fitted with an engine, and loaded with solid propellant. One of these solid propulsion engines is the P120C. It was recently successfully tested in Kourou and is the largest and most powerful monolithic solid propulsion rocket ever built. With this new rocket, ESA hopes to respond to launcher market demands. The agency is also looking for value for money. This new engine is designed with the latest immersive technology and leading-edge materials and processes. Mass production will bring down the unit cost, but the design is for both Vega C and the strap-on boosters for Ariane 6.
So certainly in the launcher sector, the competition is growing worldwide. But we believe that the European answer, the ESA answer with Vega C and Ariane 6 is the right answer. In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega C and the Ariane 6, the P120C solid rocket motor that enables the possibility to harmonize resources and to have the same motor serving the Vega C as a first stage as well as the Ariane 6 in both configuration as a strap-on boosters. So this is a very good answer to tackle the competitiveness aspect.
With Vega C, the C stands for consolidation, ESA is further developing Vega. It will add increased performance to the flexibility of the current system without increasing the costs. Today, Vega can launch up to 1.5 tons on a 700-kilometer orbit. With Vega C, it will go up to 2.3 tons. In order to increase performance, two new solid propulsion engines have been developed, the P120C and the Zefiro 40 for the second stage.
It is clear that whatever we develop has an exploitation objective. So we do not develop rockets just for the fun of it, but we develop rockets that need to be exploitable, therefore competitive in the worldwide market. And that's the way we are working hand in hand with industry to prepare them to walk on their legs in the future throughout the exploitation phase.
Further enhancements are made with Avom Plus, which is derived from the current Vega's Avom upper stage. Investing in new rocket motors also means investing in new launch facilities.
We have foreseen a lot of activities to modify the launch site from the Vega configuration to the Vega C configuration. Vega C is a heavy, larger and length launchers with respect to the Vega one. So for this reason we have to modify the hatches to the stages, increasing the diameters for what concerns the first stage.
Other changes include modified fluid services and installation of a more powerful crane needed to lift the heavier second stage of Vega C. During these modifications, the site has to remain operational for the scheduled Vega launches. In the end, the launch site will be compatible with both launchers. With Vega C, ESA is also working on related products such as the Space Rider, based on ESA's experimental re-entry vehicle IXV. It should allow for payloads to be sent into orbit and later return to Earth.
In addition to this, we have other products like a specific adapter for launching into orbit small spacecraft, so enabling the possibility of universities and research centers to access space at limited cost. So coping with the payloads which go from 1 kilogram up to 500 kilograms. We also have early elements of definition for a platform called Venus, which could allow payloads to transfer from orbit to orbit.
One unit which has been around for years and is still the Ferrari of rocket motors is the Space Shuttle main engine. Four of them will be mounted on the long-awaited Space Launch System. Reusing proven shuttle technology has saved time and money. The solid rocket boosters have been extended and tested. The Aerojet Rocketdyne RS-25 motors continue to roll off the assembly line. Fabrication of the immense components, cryogenic tanks, intertanks and fairings continues. The Orion capsule has flown once. The second flight-ready capsule is being prepared for the grand show. There is one more critical piece of kit required, perhaps one of the most important sections for keeping the astronauts alive, the service module. At Airbus in Europe, they have delivered the first flight-ready unit for the launch. The European component will house the electrical power, life support and propulsion unit for the Orion spacecraft, and like a giant pocket watch, every component is carefully and painstakingly assembled.
The European service module is part of an entire spacecraft built by an American company, Lockheed Martin, under the contract of NASA, and we are part of that. And of that spacecraft, NASA, Lockheed Martin is building. We are providing the European service module. We are providing the powerhouse of that entire spacecraft. That means we are providing the propulsion system, so the thrust to get into the dedicated orbit we would like to fly with the spacecraft. We are providing the air condition, I'm saying. That's the thermal control system of the entire spacecraft. We take care of the heat, which has been generated in the capsule, which has been generated out of several electronic components in the European service module as well. And we are making sure that that heat gets radiated into the outside of that spacecraft. On top of this, we are generating power. Our solar array wings are producing that power. We are conditioning that power and deliver that to the crew module and deliver that to the batteries with it, which are located inside the crew module. And finally, we are also providing what the astronaut need to have to live in that spacecraft. That's mainly water in terms of the consumables, and that's oxygen and nitrogen to generate the atmosphere in the crew module itself. On the power side, we are proud that we have installed hardware which has already been flown several years ago on a shuttle. So the big engine we are flying here, the OMS-E, was a challenge for us to bring that into the vehicle. This is not new technology in that sense, but the integration itself, that was really for us a challenge that was new. We're preparing ourselves to be ready for the final integration with the rest of the vehicle. And then we are ready for a test campaign in the US, which is including several environmental tests, several functional tests. That lasts a couple of months, up to that point where the NASA team is handing over the spacecraft to GSDO, to the launch campaign, so that the vehicle can be put onto the launcher, and then we're ready for flight.
The first engine is the big engine, which is coming from the space shuttle. With this big engine, we perform the big transition maneuver to go to the moon or to go back to the Earth. So we can see here the auxiliary thruster, which are red. We have 8 of them coming from Aerojet. Here we have the OMS-E, so the main engine, but without the nozzle, which will be integrated in one of the latest integration steps. We can see here the propellant tanks. We have 4 of them, 2 for each propellant.
ATV, basically the automated transport vehicle here in Europe, played a significant role in terms of opening the door for that specific joint work on that spacecraft. It also played a role that we learned our lessons with a kind of that service module. Finally, the components we have flown on ATV, there are not so many which we carry on in the Orion European Service Module. We have a couple of them, mainly auxiliary thrusters, yes, on the RCS thrusters, and also a couple of tanks like our pressure tanks, but there are not just a few items which we carry on from ATV into the European Service Module design.
The difficulty here for the human spaceflight is the change of mindset. So to think that we are here in this space mission, we are flying human, and it's not like a rocket which is only flying with a satellite. Therefore, we are putting more effort on the safety aspect. We have a lot of redundancy. Each change we introduce, the smallest change we introduce in our system has to go through the safety boards, our safety boards, ESA safety board, and then the program safety board, to be sure that we can bring the crew back home safe.
With Orion and the service module certified, the sky won't be the limit. We will see ships refueling in orbit, a gateway station with a return to the moon, then on to Mars and beyond. opening space to industry and exploration, spaceflight will become the norm rather than the exception. Mining and manufacturing in orbit, power production, and habitats. One day, it might be as easy as driving to work in that red convertible of yours.